quality water, only to flush it away to a wastewater treatment plant where we spend significant amounts of money and energy to remove 3 key nutrients, namely nitrogen, phosphorus, and potassium. Now, if we examine this waste stream more closely and we focus on the urine, we see something interesting. We see that the urine only makes up about 1% of the total wastewater in terms of volume. Yet, it contains over 80% of the nitrogen, 70% of the potassium, and 50% of the phosphorus. These are 3 key nutrients needed to make any inorganic fertilizer, but we literally flush them away every day. So how could we collect this precious resource? Well, we could collect it in something called no-mix toilets. And like the name suggests, it essentially doesn't mix the feces and the urine, and it separates it at source. Or we could use urinals. So urine collection and treatment has been conducted in Switzerland, and this is where I got into urine of all things. And actually in this novel building, they have no-mix toilets and urinals, and they divert the urine and they collect it in 2 storage tanks. And the beauty about this project is they are currently making a liquid fertilizer, and they've started a startup to sell this liquid nitrogen-based fertilizer. If we look at the global trend, we see that this kind of work is actually being implemented in a number of places, and even in South Africa. Now, this is an example of urine collection in South Africa for a new building built for Ens-O by Growthpoint. And it was essentially based on the urine-related work that we're doing at the University of Cape Town. So conventionally, the urine would be connected to a normal main sewage line. But in this building, the urine is diverted in a dual piping system and collected in a storage tank for subsequent fertilizer production. But urine collection is not without its challenges. For example, you would have to retrofit existing buildings if you wanted to implement these systems, and that would be expensive. Concentrated urine, when you send that now is rich in nitrogen can be further concentrated using something as simple as reverse osmosis, which we use for desalination. And if we achieve an 80% recovery, we essentially would be using the urine to produce water along with a liquid fertilizer. And this liquid fertilizer could be sold for as much as 120 Rand per litre, equating to about 24,000 Rand per day. And this is because niche fertilizers can be sold for up to 800% more than bulk fertilizers. And more importantly, this entire process would not have a waste stream. So the future of urinals would consist of something like this, where you have a removable container. Now, this is an example of a design with Denka, which is a design company based in Cape Town, that has currently helped us design this. And don't worry, ladies, unisex urinals do exist, so we haven't forgotten about you. So this brings me to the other innovative system that we've been looking at, is actually growing biobricks from urine. And the way this process works is essentially you take loose sand, you colonize it with special bacteria, which produce an enzyme called urease, and then you add your urea and your calcium, which essentially comes from the urine. And what happens is that this produces calcium carbonate. And calcium carbonate is a cement that essentially glues the loose sand particles together, and eventually you get a solid forming. It's very similar to how calcium carbonate caves, or calcium carbonate shells, or even calcium carbonate coral reefs are made. And so you can grow it in any shape you want, in this case a mold of a brick. And the way it works, you add your material and you simply pump the urine through, and eventually you get a solid forming of the shape you want. So you might think this is outlandish, but consider this. Biomason is a US-based company that is currently growing 2,500 bricks a day using this process, although they don't use urine. So other considerations is the transportation logistics. How do we transport the urine to a resource recovery plant where we produce the fertilizer and the biobricks? And in terms of green star rating, they typically rate buildings according to energy, water, and materials or emissions, but what about nutrients and wastewater? So the buildings of tomorrow, or the cities, would implement these kind of systems where you recover water and you also produce water, energy, as well as fertilizer for food consumption, and even biobricks. Essentially, the buildings will become resource recovery plants. I leave you with this final quote. Pollution is nothing but the resources we are not harvesting. We allow them to be dispersed because we've been ignorant of their value. Thank you.